Hello everyone, this is Ta-Ying. Today, I'll be presenting to you our paper, Learning Continuous 3D Words for Text-to-Image Generation. This work is done during an internship at Adobe Research. Current diffusion models for image generation, despite their tremendous generative capabilities, are very difficult to control, especially in terms of abstract, continuous attributes like time of day illumination or non-rigid shape changes. Say you want to generate a horse with a specific orientation and time of day illumination, but you only have a dog mesh that you can simulate the orientation and illumination from a rendering engine. Then, using methods like ControlNet will result in generated images where the horse is tightly entangled with the dog's shape and geometry. In this work, we present another approach to tackling this problem by presenting continuous 3D words, a way to encode abstract, continuous, 3D aware attributes such as illumination, deformable shape changes, or camera parameters into sliders. These sliders can then be used jointly with other texts to gain fine-grained control over image generation. The following figure presents our method. Given one of very few available meshes, our continuous 3D word is learned through a two-stage fine-tuning approach. In the first stage, the goal is to learn the training mesh identity so that we can disentangle this identity from the continuous attributes, such as illumination and an orientation in this case, that we are trying to learn. To do so, we follow personalization techniques of DreamBooth to first learn a word token, OBJ, to represent the mesh rendered under varying illumination and orientations. After learning the token, we can then add an additional MLP, G, that takes the numerical values of the attributes we're hoping to learn and outputs a feature the same size as word tokens. We jointly feed these features with the remaining prompts describing the image and the token we learned in the previous step into the diffusion model during denoising. Since the geometry of the mesh is learned during stage 1, stage 2 inherently learns to disentangle these attributes from the object identity. Finally, during inference, we can now replace the OBJ token and generate other images, such as a horse, while controlling their 3D aware attributes with the learned MLP G. We show both qualitative and quantitative results of continuous 3D words against ControlNet of different strengths. Here, you can see that a strong guidance from ControlNet leads to less generalization capability, where the shape is constrained to what the initial condition looks like. On the other hand, a weak guidance gave too much flexibility, and therefore the generated images do not follow the other conditions such as camera parameters, orientations, wing pose, etc. Our methods perform better across both single and multiple learned concepts in both our user study and qualitative results. Finally, continuous 3D words can also be applied for image editing simply by encoding a real-world image with an extra rare token via DreamBooth. Then we only have to use that token in conjunction with our continuous words to generate the edited image. We show 8 examples in this figure, changing illumination, wing pose, and object orientation. While our approach is focused on enhancing text-to-image, given the capabilities of real-world image editing, we can also use the same setup to provide a comparison with methods such as 0123 for orientation-only setup. More importantly, our method allows controls beyond orientation changes without relying on massive 3D datasets. Thank you for listening to our presentation. Feel free to scan the QR code at the bottom left for more interactive results on our website.